The work described in this video was supported by the United States Department of Energy through the U.S.-China Clean Energy Research Center on Clean Vehicles. The motivation behind this work is to ensure functional safety in road vehicles, a very important consideration in today's vehicles to meet stringent performance, reliability, and safety standards. The method developed in the study follows a V-diagram in which one progresses from requirements definition to the development of fault models, to the development of diagnostic strategies, and to the evaluation of these strategies using model-in-the-loop, software-in-the-loop, and hardware-in-the-loop methods, eventually leading to in-vehicle calibration. The algorithms developed as part of this project were demonstrated on the EcoCAR 2 plug-in hybrid electric vehicle prototype developed by students at The Ohio State University. The specific application of functional safety that is demonstrated in this video pertains to torque security, that is, the ability to deliver the required torque securely and safely under all circumstances, preventing the possibility of any sudden unintended accelerations. One of the key elements in our demonstration program is the use of hardware-in-the-loop testing methods that allow the control designer to anticipate how the control and diagnostic algorithms will interact with the vehicle and eventually leading to the development of real-time computer control code.
My name is Jiyu Zhang. I'm a PhD student at Ohio State University, and this is my colleague Tianpei Li. We are developing some fault diagnostic and fault mitigation strategies to deal with electrified vehicle torque security problems. Torque security is one of the important issues for future automobile development, such as in hybrid and electric vehicles. We are using the EcoCAR 2 vehicle as our case study to demonstrate our diagnostic and fault mitigation strategies. An EcoCAR 2 vehicle is a plug-in hybrid electric vehicle developed by the EcoCAR 2 team at the Ohio State University Center for Automotive Research. So we are going to implement our diagnostic and fault mitigation strategies as part of the supervisory controller in the vehicle. And before we can actually implement the strategies in the vehicle, we are going to conduct hardware-in-the-loop experiments to show the effectiveness of the diagnostic and mitigation strategies. And today I'm going to show you an online demonstration of how we conduct the hill tests. Here is the configuration of the hill system. The bigger box is the D-Space simulator, where we put the models of the entire EcoCAR 2 vehicle in it. And the smaller box just above the bigger box is called the micro-out box. This is the place that we implement the supervisory controller. The fault diagnostic and fault mitigation strategies we developed are included in the supervisory controller and therefore is implemented in this micro-out box. The hardware part in this hill system is the pedal assembly. As we are going to implement the diagnostic algorithms in the EcoCAR 2 vehicle, the pedals we are using are the same pedals that are currently used by the EcoCAR 2 vehicle. Faults we are considering here are the mechanical stiction of the accelerator pedal and the faults in one of the accelerator pedal sensor or brake pedal sensors. The pedal assembly sends out the pedal signals to the supervisory controller, which converts the pedal signals into a torque request, and then sends it to the electrified powertrains included in the hill box. The micro-out box and the D-Space simulator are communicating through the CAN bus and a set of analog digital channels, which are wired by these lines here. This laptop is communicating with the micro-out box through control desk software, where we can control the faults. Faults are injected by modifying the outputs of the sensors. As you can see on this display, we can control the faults through these on and off switches, including the mechanical stiction faults for the accelerator pedal or brake pedals, as well as the sensor faults for the 4 sensors. The hill simulator is communicating with this computer to display the results through the control desk software. The monitor mimics the vehicle dashboard to display the velocity, electric motor speed, torque, and etc. The brindle and ignition switch will simulate the starting and stopping sequence of the vehicle. These are the plots showing you the vehicle speed, electric motor torque, accelerator pedal, and brake pedal positions, comparing the pedal commands before and after control. The diagnostic results will be displayed by these 6 warning lights. If the controller detects a specific fault, the corresponding light will turn red, meaning that we have detected and isolated a fault. So now we can begin to conduct the hill tests.
First of all, we will start the vehicle. We first ignite the vehicle, and you can hear the sound that mimics the engine noise. That is just to show the vehicle is started. And then we can press the brake and put the pedal from park to drive. Then the driver could play with the accelerator pedal to let the vehicle accelerate. The driver can either arbitrarily press the accelerator and the brake or intentionally follow a driving cycle. Now we could start injecting faults. We start from the accelerator pedal mechanical stiction fault. By mechanical stiction, we consider the accelerator pedal gets stuck at a partially depressed position while the driver releases the accelerator pedal. After a few seconds delay, the warning light corresponding to this fault turns red. That means a fault is detected, as can be seen from the two plots on the upper middle corner. After the stiction fault is detected, the controller immediately reduces the accelerator pedal position until the driver realizes the fault and presses the brake pedal. By then, the accelerator pedal position is overridden and is immediately set to 0. Next, we will show you sensor fault detection and isolation. We consider the case where the characteristic of accelerator pedal position sensor 1 changes due to a short circuit fault in the variable resistance at 0 to 20% position inside the APPS1 circuit. As can be seen, the light corresponding to the accelerator pedal position sensor faults immediately turns on, meaning an APP sensor fault is detected. However, before the brake pedal is pressed, the controller has not isolated which one of the APPS sensors are faulty. But this will inform the driver the occurrence of a fault and remind the driver to press the brake. After the brake is depressed, the APPS1 sensor fault light is turned on, meaning the fault is isolated. The two plots shown on the lower middle of this screen compares the outputs from the two APPS sensors, or BPP sensors, as well as final outputs from the fault mitigation controller. As can be seen, after the APP sensor fault is detected, but before the particular sensor fault is isolated, the controller takes the minimum value of the two APP sensor outputs for the sake of safety. After the fault is isolated, the controller will switch to the other healthy sensor and takes the corresponding value from the healthy sensor outputs. There are additional lights on the right corner of this screen to show the sensor operating modes in case that any sensor faults occur. Green means on, red means off. That is, if one of the sensor faults is detected and isolated, the corresponding sensor light will become red to show that we're disabling this sensor and switch to the other healthy sensor.
The work described in this video was carried out by the Ohio State University Center for Automotive Research in collaboration with Beijing Institute of Technology and Hefei University of Technology. We gratefully acknowledge the support of partners Delphi, Ford Motor Company, D-Space, and the MathWorks, and we recognize the outstanding effort of the U.S. Department of Energy and of the University of Michigan and Tsinghua University in leading the U.S.-China Clean Energy Research Center between 2011 and 2016.